Welcome back, everyone. Today, we are unpacking a massive topic for this explainer. We are diving into Chapter 3 to channel our energy into something that literally powers our entire modern world, current electricity. We're going to break down the fundamental principles of how electricity flows, taking you on a journey from the macroscopic phenomena you see every single day, right down to the microscopic traffic jams happening inside your charging cables.
Here's our roadmap for explaining the chapter today. First, the flow of charges. Then, Ohm's law and resistance. Third, the secret life of electrons. Fourth, powering up. Fifth, cells and internal resistance. And we'll wrap things up with Kirchhoff's rules. Let's jump right in. Section 1. The flow of charges, from lightning to rivers.
You know, there is a totally fascinating contrast between natural and controlled electricity. We've all seen lightning, right? It's this disastrous, unsteady, and completely chaotic flow of charges rapidly jumping from the clouds down to the earth. But obviously, that's not what's powering your smartwatch. Contrast that chaotic strike with a cell-driven clock. That is a steady, controlled, river-like smooth flow of charges. And for this explainer, we are focusing entirely on that smooth river, steady electric currents.
At its absolute core, electric current, which we represent with a capital I, is simply Q divided by T. It's the net amount of positive charge flowing across a specific area in a forward direction over a given time interval. Think of it like measuring how many gallons of water flow past a certain point in a river every single second. It's that simple. And, of course, in the standard system of units, we measure this steady flow in amperes.
Moving to Section 2, Ohm's law and resistance, the traffic rules of circuits.
So, the crucial rule governing all this flow? It's that classic equation, V equals I times R. Discovered by G.S. Ohm way back in 1828, Ohm's law dictates that the current flowing through a substance is directly proportional to the voltage applied across it. But this flow doesn't just happen freely, right? It is actively slowed down by R, the material's resistance. If voltage is the water pressure pushing through a pipe, resistance is all the rocks, bumps, and narrows slowing that water down.
And different materials handle this electrical river in distinctly different ways based on their resistivity. Conductors, like copper, have incredibly low resistivity and they generally obey Ohm's law perfectly. Insulators are on the opposite end, super high resistivity, basically blocking the flow altogether. But check out semiconductors, sitting right there in the middle. They have medium resistivity, but interestingly, they can deviate from Ohm's law entirely. Their voltage to current relationship can be completely nonlinear. It's a great reminder that Ohm's law isn't some universal law of nature like gravity. In fact, in tons of modern electronic devices, this simple proportional relationship actually breaks down.
Section 3. The secret life of electrons, a microscopic deep dive. Okay, I really want you to think about this question for a second. How fast do electrons actually move through a typical copper wire? I mean, when you flip a light switch, the bulb instantly pops on. Because of that instant reaction, it's so natural to assume that electrons are zooming through those wires at the speed of light.
But the microscopic reality is shockingly different. We're talking a few millimeters per second. Literally, that is it. As calculated in the source text, the actual drift speed of electrons carrying a standard current is unbelievably slow. Why? Well, because inside that solid metal wire, electrons are definitely not traveling in a straight line. They are constantly bouncing and colliding with heavy metal atoms in completely random directions. So while they do have really high thermal speeds bouncing around, their net forward drift, the part actually pushed by the electric field, is just a tiny slow crawl of a few millimeters per second.
All right, Section 4, powering up. Where does the energy actually go?
Let's look at the math of that energy transfer. We call this ohmic loss, where power equals V squared over R, or alternatively, power equals I times V. As those electrons slowly bump and crash their way through the internal resistance of a wire, they inevitably lose energy. And that energy doesn't just vanish into thin air, it's dissipated right into the environment. This actually brilliantly illustrates how a traditional electric bulb works. The high resistance of the bulb's filament causes so much ohmic loss that it heats up to incandescence, radiating out both heat and light. It's literally atomic friction at a microscopic scale lighting up the room.
Which brings us to Section 5, cells and internal resistance, the somewhat messier reality of power sources.
Let's break down the basic anatomy of an electrolytic cell. You've got your positive and negative electrodes, and they're immersed in an electrolytic solution that's actively exchanging charges. This setup provides what we call electromotive force, or EMF. represented by the Greek letter epsilon. Now here's a really fun fact. EMF isn't actually a force at all. It's simply the maximum potential voltage difference between the two terminals when the circuit is completely open. And notice that final point, internal resistance, marked as R. Yep, even your power source has its own built-in speed bumps. Because of that internal resistance within the electrolyte itself, we get this equation for real cell voltage. V equals EMF minus the product of I and R. Practically speaking, this means the actual voltage you get out of a working cell is always going to be slightly less than its theoretical maximum EMF the moment current actually starts flowing. The battery itself resists the flow of its own charges, creating a small internal voltage drop.
Finally, Section 6, Kirchhoff's Rules for Circuits, Navigating Complex Intersections.
As the chapter states perfectly, two rules, called Kirchhoff's rules, are very useful for analysis of electric circuits to determine all the currents and potential differences. Simple formulas for series and parallel resistors are great for basic setup, sure, but when you're looking at a real-world circuit with multiple intersecting branches and multiple batteries, those simple formulas just aren't enough. We need a much more robust system to untangle the math.
And here is that system, cleanly laid out in 2 steps. Step 1, the junction rule. The sum of currents entering any junction exactly equals the sum leaving. Think back to our river analogy again. If a river splits into 2 streams, the water doesn't magically disappear. 3 amps flowing in means 3 amps must flow out. It's just the conservation of charge. Step 2, the loop rule. The algebraic sum of changes in potential around any closed loop is 0. This one is all about the conservation of energy. If you hike in a loop and end up exactly back where you started, your net change in elevation is 0, right? The exact same logic applies to voltage dropping and rising in a closed circuit loop.
So, as we wrap up this explainer, I want to leave you with a quick thought. Look at the devices around you right now. Can you picture it? The silent, millimeter-per-second drift of literally billions of electrons currently powering your world. The next time you switch on a light, check your phone, or plug in a charger, take a brief moment to appreciate that slow, steady, microscopic traffic jam and the absolutely beautiful rules of physics making it all possible. Keep questioning, keep learning, and I'll catch you in the next one.